Welcome to my video course on mastering ERTMS and ETCS signaling systems. Right off the bat today, we're diving straight into the absolute core mechanics of modern railway safety, which is automatic train protection. We're going to explore exactly how modern trains use math to predict danger and how they automatically step in to take control when it's necessary. Let's get right to it. So here's our syllabus for today. First up, we'll cover ATP concepts. Then we'll look at preventing SP incidents. From there, we'll break down the safe braking curve, move on to ETCS train supervision, and wrap up with the driver-machine interface.
All right, Section 1, Introduction to ATP Concepts. To truly master modern signaling, we kind of need to take a brief look at the history. Back in the early 1980s, European railways realized they had to go way beyond basic trackside signals and, well, just relying on human vigilance. That massive realization led directly to automatic train protection, or ATP. Think of it as a relentless, active safeguard. It's constantly monitoring the train's speed, and it will apply automatic braking if warnings are ignored. Now, early systems did use target speeds and audible warnings, but the game changer was that if a driver missed them, the system didn't just log a mistake on a computer somewhere, it physically intervened. It's an engineering solution specifically designed to step in exactly when human operation fails.
Moving right along to Section 2, Preventing SPA Incidents.
Now, you might be asking yourself, why is this automatic physical intervention absolutely crucial? Well, it all comes down to eliminating literally one of the most severe, high-stakes safety breaches you could possibly have on a railway, a SPAD, or signal passed at danger. This nightmare scenario happens when a train completely fails to stop at a red or even a dark, unlit signal. And remember, an unlit signal must always be interpreted as an absolute stop command. Passing it means that train is barreling into occupied or completely unverified track. The potential for a catastrophic collision there is just immense. So ATP serves as the ultimate non-negotiable line of defense against this specific hazard, as well as general overspeeding.
Which brings us to Section 3, the safe braking curve. Okay, we know the system stops the train, but how exactly does it predict danger before it actually happens? It's like a giant, real-time math puzzle. Take a look at this model. On the horizontal axis, you've got the distance moving toward a target point. That could be an obstacle or a red signal. On the vertical axis, you have the train's speed. What happens is the onboard system continuously calculates what we call a protection curve. It uses three absolute vital metrics to do this: the target distance ahead, the current speed of the train, and the physical braking characteristics of the vehicle itself. This curve dictates the absolute maximum safe speed the train can travel at any given split second to guarantee it can stop in time. And the onboard computer, it's literally recalculating and redrawing this curve instant by instant. The logic here is beautifully simple. If you operate below the maximum permitted speed, safely tucked under that curve, everything is totally normal and the driver keeps full control. But the second the train exceeds that maximum defined boundary and pushes up into overspeed territory, boom, the automatic brake immediately engages to force the speed back down into the safe zone. It just removes human guesswork entirely.
Let's move to Section 4. ETCS train supervision.
Let's look at how this mathematical braking model is practically applied in our modern interoperable networks. In ETCS Level 2, dynamic train supervision means the onboard computer is constantly comparing the actual speed against several heavily calculated limit curves to enforce what we call the most restrictive speed profile, and it happens through a very strict escalation sequence. It starts off mildly with a pre-indication, just to warn of an upcoming braking zone. Then you get an indication as the speed nears the limit. After that is the permitted speed, which is the absolute cap. If the driver ignores that cap, we cross the line into active physical intervention, warning, service brake intervention, and finally, emergency brake intervention.
Let's zoom in on those critical intervention steps because honestly, this is where the machine literally takes over the driving. Step 1 is the warning. Cross the warning curve and a loud audible alarm sounds. The driver must start braking right now. Step 2 is service brake intervention, or SBI. If the driver ignores that alarm, the system basically assumes incapacitation or a major error, and it automatically applies the service brakes until a safe speed is reached. Step 3 is the big one, emergency brake intervention, or EBI. If the train speed is so extreme that it blasts past the SBI limit entirely, full emergency brakes are deployed. It's just a flawless automated escalation from a human warning to total machine takeover.
And finally, Section 5, Driver-Machine Interface.
So all of these insane split-second calculations have to be communicated to the human operating the train instantly, right? That all happens on the cockpit display, known as the DMI.
usually via these circular speed arcs. The system relies on a very strict color-coded matrix. When the display is gray, it's low priority. No immediate action is needed from the driver. When it shifts to yellow, urgency increases to average, and the driver needs to take appropriate action, like applying the brakes. But if that dial turns orange, that is a high priority urgency. Immediate corrective action, like heavy braking, is demanded right then and there before the automated systems we just talked about step in and do it for them. This whole journey through automatic train protection really leaves us with a provocative scenario to think about. As we push for even higher speeds and tighter headways to increase our infrastructure capacity, how will train supervision evolve to completely eliminate human error once and for all? We've seen today how dynamic speed monitoring creates this incredible mathematical safety net, and the future of high-speed rail depends entirely on mastering these very concepts. Thanks, we can see you next video.